Okay, so I'll get started with the class. So the topic for this week was linear regression. At the very outset, I would like to ask the people who are present here whether I believe there are some concepts from linear algebra that are useful in this particular week. So are you all comfortable with the basic concepts of linear algebra? I mean, I am asking this because otherwise after going through these questions I will give you a basic understanding of how linear algebra, I mean the basic tools which might be useful to you in this course. So are you comfortable with that, or should I hello, there is some sound but I can't hear an answer. So okay, so that means that I would take that as a yes, that you are comfortable with the things. Okay, so I'll get started with the questions. So for linear regression, the first question says, yeah, so okay, this is pretty big. Okay. This is Yeah, so the first question says that the parameters obtained in linear regression, it can take any value in the real space as strictly integers, always lie in the range of 0 to 1, and can take only non-zero values. So what do you think is the answer for this? Hello? Yeah, Sanjeev says, okay, you are unable to read it, is it? So should I, so is it better now? I mean, is the screen, is it visible, the question? Yeah, so the answer, as somebody said, it's A. We are not constraining the parameters of the linear regression to take any of those other three values like integers or always lie in the range of 0 to 1 and so on. So they can take any value in the real space. So that's pretty simple. The second question is like, suppose that we have n independent variables. So you have n independent variables and the dependent variable is y. So that means you have taken these many independent variables and you are trying to predict what the value of y would be. Now imagine that you are applying linear regression by fitting the best fit line using the least square error on this data. That is how you are fitting the data, and you found that the correlation coefficient for one of its variables, so any of these variables, so let's say here for an example it's given as x1 is minus 0.005, and this correlation coefficient is actually quite low. This means that y does not depend on x1 that much. So in this case, what do you think if we regress y on x1, which means that if I use x1 to predict y, does it explain, so is the first option true or is the second option true? So the last option is obviously not true. So I mean that given data is insufficient to determine if regressing y on x1 explains away y or not. This is not an option, because I mean, of course, if you have been given such a strong information about the dependence of y on x1, then of course the data is sufficient to predict whether x1 the first two options to be correct, any one of the first two options to be correct. So what do you think, between A and B, which one is the correct option? So the first option says that regressing y on x1 mostly does not explain away y, which in other terms, I mean, intuitively you can say that if you are using y1 to predict x1, if you are using x1 to predict y1, you are not able to explain it properly. That is what the first option means. The second option means that if you are using x1 to predict y, you are able to explain y very well. So which of the two options should be correct, given that the correlation coefficient is quite low? Yeah, again it's A. So A is the correct option since y has such a low correlation. Yeah, so somebody is saying, can you please explain least square error also? Yeah, I will explain it in the next problem itself. So if regression on y on x1 mostly does not explain away y, which means that y and x are not related in any sense. I mean the relation between x and y is very low, hence you can as well remove x1 and you will not lose any information to predict y. So that is the second question. So brief go through basics. Yeah, I will go to the questions and then you can ask me any questions that you might have and I would be happy to take them. Okay, so consider the yeah, these are all uploaded to YouTube and I believe NPTEL will give you access to that. So so I mean once I record this will be recorded and I will send this to YouTube and the YouTube link will be provided to you. Okay, then considering the 5 training examples, this is a slightly I mean tricky example in the sense that, okay, let's go through the problem first. So consider the following 5 training examples. So you have been given 5 training examples and these are the x and y values. So these are all one dimensional and we want to learn a function fx of the form fx equal to ax plus b, which is parameterized by a and b. Using mean squared error as a loss function, which of the following parameters would you use to model this function to get a solution with a minimum loss? So the question is not asking you to find out the true values of a and b, which would I mean the true values of a and b which would come out if you do the entire calculation, because the calculation itself will become a bit tedious. So what it is saying is, between all these values of a and b, which is the best set of value that give you the minimum least square loss. Okay, so that is the question that has been asked here. So let's compute the value. So let's say I am taking the value of 4 and 3. Okay, so so let's say my a is 4 and b is 3. In this case, for the first example, yeah, and the thing that you are computing is ax plus b. Keep that in mind. So for the first example, the ax plus b would give you 4 into 2 plus 3, which is 11. In the second case, ax plus b will okay, so it will be just 15. Yeah, 15, then 19, 23 and 27. So these are the 5 y values, y hat values, if you may call them. So these are your predicted values. Okay, these are your predicted values, and the actual values were 7. These are the actual values that I am writing here. The actual values are 7, 8.6, 3, 11.5 and 22. Okay, so you are incorporating a error here of, since this is a least square I mean mean where is it? This is a mean squared error, so you have to take a square of the error. So that means this will be 4 square, which is 16. I am considering the error terms here. This will be 6.4 whole square. I won't do what is 6.4 whole square. The next is 16 square. The next is 11.5 whole square, and the last is 25, which is 5 square. So this way you can find out what is the total loss that you will incur if you start using 4, 3 as your parameters. And I'll do another one for you, and I'll leave the rest, the last 2 for I mean you can do that yourself. So for a equal to 1 and b equal to 4, which is a second option, you can find that, okay, the first option would be ax plus b, which is a into a 1 into 2 plus 4, which is 6. Okay, here a is 1. Okay, then this will be 6, 7, 8, 9, 10, right? This will be 6, 7, 8 and 8, 9 and 10, yeah. And here for the first case you will incur a loss of 1. The second case you will incur a loss of 1.6 whole square. Third case you will incur a loss of 5 square. In the fourth case you will incur a loss of 2.5 whole square. Last case you will incur a loss of 12 square. So in this way you can proceed for the other two also and sum them up. So the total sum will be your error. So just by looking you can understand that the second option is better than the first option for sure. And indeed you will find that if you do the calculations for the other two, you will find that 1, 4 is the correct option. You can do the other two by yourself, and 1, 4 will indeed be the correct option in this case. Okay, I hope that was I hope that was clear to all of you. Okay, now let's go for the fourth question. Okay, so the fourth question is like the so the fourth question is something like the relation between studying time in hours, and that is denoted by H, and the grade on the final examination, and that is denoted by grade. Problem in a random sample of students in some class was found to be this. So this is the relation that you have found between grade and studying hours. And how will a student's grade be affected if he studies for 4 hours? So again, this question is not I don't think it is framed properly. So it would have been better if the question was like, how will a student's, so this question seems like you put H equal to 4 and whatever grade comes it will, so that is the answer. But the question that is actually that it is actually trying to ask is, suppose you have already studied, some student has studied for H1 hours and now he or she studies for H1 plus 4 hours. What is the grade that might improve because of this? And that is pretty simple. Like you can see that since H is multiplied with a term of 15.2, it will go up by 60.8 points, because 15.2 into 4 equal to 60.8. So the C is the correct option. I think these are pretty simple things. This is just normal. These are nothing new to all of you, I guess. So so I'll come to the fifth question. So the fifth question is something which you might have heard for the first time in this course. So there are two types of regression, as you might know now. There is ridge regression and there is lasso regression. So I can talk about this a bit more after I finish the class, because maybe there will be some questions that might be coming, you might have regarding both of them. So L2 loss or L2 regression or ridge regression, it is also called L2 regression. So what it does is it tries to minimize the 2 norm of something. So of your parameter vector, of the vectors that you are after, those vectors, it will try to reduce the 2 norm of that. And what lasso regression will try to do is it will try to reduce the 1 norm of that. So these are the two ways in which you can add regularization to your model. And so this question is about both of them. So first is ridge as a sparsity constraint, and it will drive coefficients with low values to 0. If you have gone through the lecture material, I think you would be able to answer this. So can somebody answer whether the first thing is true or not? Does ridge regression improve sparsity, encourage sparsity in your solution? Okay, I'm not getting an answer. Okay, so ridge basically doesn't have a sparsity constraint. It will try to put the 1 norm, it will try to put the 2 norm of your close to 0 but not exactly 0. I don't know whether it is the correct way to put that. That's the correct way to put this. Basically what ridge regression will try to do is it will try to reduce the 2 norm of your 2 norm of your variables. So if you consider a vector, let's say if you consider a vector, is the question readable to everybody else? Hello, is my screen visible and is everybody able to read the question? Yeah, so somebody who is not able to read the question, I suggest you change something. So yeah, I can't zoom it anymore because then it will go, I mean it will be difficult for me to write anything, so I can't zoom anymore. So if you have joined on a mobile, then you can switch to a laptop maybe. Okay, so yeah, so the 2 norm for this particular vector, let's say I have some vector which is 2 dimensional. The 2 norm square for this vector, or the 2 norm for this vector, would be root 5, which is 2 square plus 1 square, and ridge regression will try to reduce this root 5. Okay, so ridge regression, so the ridge constraint or the 2 norm constraint will try to reduce this to 5. So you see that okay, let's give another example. Let's make it very big, then I guess you will understand. Okay, let's say I have a vector which is 1000 and 1000. So this is one vector. I mean, you might, yeah, you will have recordings of this live session. Okay, so you have 1000 and 1000. So the 2 norm of this vector would be 2 into 1000 square and a root of that. So that is what the 2 norm would be. Now suppose this comes down to 999 and 999. Okay, and the 2 norm of this vector would be 2 into 999 square, the root over of that. Okay, and this is one case. This is one case. The other case might be you have a vector which is 1 1, okay, and you are and you can reduce it to 0 0. So in this case the this will be 2 into, this will be just be root 2 and this is 0. So you see that, okay, now let's consider L2 square norm. It's basically the same thing. So in one case you are going from 2 into 1000 square to 2 into 999 square. In the other case you are going from 2 to 0. Is this clear to everybody that what I am doing now, is this making sense, or should I go over this again? Okay, then I am not getting any questions, which is making it difficult for me to understand whether this is understandable to you all or not. Anyway, so I will go along, and so yeah, I mean, you can ask the NPTEL people, they will give you the recorded sessions of all these sessions, I mean recorded version of all these sessions. I am recording this and I will put it to YouTube, you can watch in YouTube. Okay, so where was I? Okay, so for L2, the first option is, I mean, when you are going from 1000 to 999 999, your loss is reducing by 1000 square minus 999 square into 2. Okay, and if you are going in this case, the 1 1 to 0 0, your loss is just reducing from 2 minus 0, which is 2. Okay, so obviously you see that L2 will prefer this particular thing, because the reduction in loss is much more in the top case. However, if you have okay, let's make this something else. Okay, so yeah, so L2 will prefer this. So it is not like it will try to move 1 1 to 0 0, but it will just try to reduce 1000 to 999 999. Okay, so that is why L2 is not considered to have a sparsity constraint. ridge regression doesn't have a sparsity constraint. So the first statement is false. Now lasso has a closed form solution for optimization problem, but this is not the case for ridge. That is obviously false, because you know that lasso regression, which is x, lasso has this mod thing going on. So if you plot the mod of x, it will be positive x on the positive side of the x axis and negative x on the negative side of x axis, and at 0 0 this function is not differentiable. So obviously this function is not differentiable, and therefore you can't get a closed form solution for the optimization problem. You have different iterative methods of solving this. The second question is, ridge regression does not reduce the number of variables since it never leads the coefficient to 0 but only minimizes it. This is actually true. As we just saw, it never leads the coefficient to 0 but it only minimizes it, and since the coefficient of none of the variables are turning to 0, we cannot reduce the number of variables using ridge regression only. So that is true. And the last point is true. Last point is largely dependent on how we solve lasso, since that was not taught in this particular course. Therefore you just take this at the face value that when we have collinear variables, since what lasso regression does is it tries to put one of the variables to 0, it will select one of them randomly. Okay, so that is how lasso regression will work. Okay, so I hope that was clear. Okay, then coming to question number 6, we have assertion reason. So the first thing is, orthogonalization is applied to the dimension in linear regression. So if we are applying orthogonalization to the dimensions in linear regression, then that means that each of the different dimensions are becoming independent of each other, and moreover, not only are they becoming independent of each other, they are also becoming orthogonal to each other. Orthogonal means they are not affecting one another. So if that is the case, then we can just go ahead and do a univariate regression in each orthogonal dimension separately to produce the coefficient. This is a direct this was taught directly in the class, so there is nothing much to explain here, and therefore the first option is true. Both of the statements are correct, and R is the correct explanation for A. Okay. Then finally we have the last two questions again. Statement A and B are both of them, if you go through the lecture, then there are just two ways of how to do a stepwise regression or subset selection. So basically they have just flipped the two things. So in forward stepwise selection, what we do is we first take a variable, we do a regression on that variable, then we take another variable and we try to do a regression with those two variables in one go. Okay, somebody is asking a question, is it? See. Okay, Jatin is having trouble understanding the lectures of NPTEL. For YouTube channel I can't recommend, but I would definitely recommend you asking me more questions, asking the other TAs more questions, and that might help you. You can also go through the lectures, the book that has been suggested in the lecture, and that might help you as well. So yeah, these lectures are quite good, so you can try to understand, you can ask us questions, we will try to help you in every possible way. Okay, so in forward stepwise what we do is we add variables one after the other, and we have the best fit till then. So that is what forward stepwise is about. And forward stagewise is something which has been mentioned in statement A, that is, at every stage we choose a variable which has a maximum correlation with the residual, then the residual is regressed on that variable and it is added to the predictor. So okay, I forgot to put the options. Actually both these statements are true, are false. So those were the options, I believe. So both the statements are false. Okay, and so the final thing is about how to solve a linear regression model. So we have a linear regression model which has okay, let's go through this. Like y has a0 plus a1 x1 plus a2 x2 up to a of xp is to be fitted to a set of n training data points having p attributes each. Okay, so that means I have y1, I have y2 up to yn and y capital N. So this is a n cross 1 vector, and I have x which is n cross p. Okay, so let's say I have n cross p. So again I have x11, x12 up to x1p, x21, x22 up to x2p, and so on, xn1, xn2 up to xnp. Okay, this is my X matrix, and this is n cross p. It has n rows and p columns. N cross p. Let X be a n cross p. So n cross p p1 vectors of input augmented. Okay, it has been augmented by 1 also, is it? Okay. Let X be a n cross p plus 1. Okay, so let's just augment this with 1. So this is n cross p plus 1, and so y is a n cross 1 vector of target values, and so if this is n cross p, I will have to multiply it with something which is p plus 1 dimensional. So I have theta 1 up to theta p plus 1. So this is y, this is x, and this is theta. Okay, these are this is what is given to you, and theta equal to p plus 1 vector of p plus 1 vector of the values a0, a1 up to ap. Okay, now if the sum error is minimized for obtaining the optimal regression, which of the following equation hold? Okay, so see here what we can do is let me see how to put this properly. Okay, so okay, let's go through this equation step by step, because I believe it will be helpful. So you have y1 to yn, and this will be x11 theta 1 plus x12 theta 2 plus dot dot x1p theta p plus theta p plus 1. I hope this is clear to all of you. I mean, I'm just multiplying this matrix by this vector. So x21 x plus x22 theta 2 plus x2p theta p plus again theta p plus 1, and so on. We have xn1 theta 1 plus xn2 theta 2 plus xnp theta p plus theta p plus 1. Okay, so y1 up to yn are your targets, and this is something that you have got. And now what you need to do is, you see they have written that if the sum squared error is minimized for obtaining the optimal regression model, which of the following equation holds? So for each of these n examples, you will need to calculate the mean squared error, and you will need to calculate the squared error and take a mean of that, and you will need to find out the solution for that. So let me again now do it for each example, and then I will convert this into a matrix notation, and I think that would be better for I mean that would be easier to solve. So the error that is coming out of the first, for this particular example, the first one is as follows: x11 theta 1 plus x12 theta 2 plus dot dot x1p theta p plus theta p plus 1. Okay, so this is the square error that is coming out of the first example. Similarly, for the second example, that is x21 theta 1 plus x22 theta 2 plus dot dot x2p theta p plus theta p plus 1 again. Okay,
can you please share your YouTube channel link for checking the previous sessions?
Yeah, I'll paste that towards the end maybe. Okay, now let me complete this, and yn minus x n1 theta 1 plus x n2 theta 2 plus x n p theta p plus theta p plus 1. Okay. So these are the errors that you are encountering for each of the n examples, and now you need to minimize, I mean you need to write this in a proper way so that you can find out what the theta p's are. Of course you can go ahead and do a derivative with each of the different parameters. There will be n p plus there will be p plus 1 parameters that you can obviously do, but that would be very cumbersome. And so let's just see, okay, let's just see what I mean how you can write this. So this entire thing, I mean let me mark it, this entire thing which you are seeing here, okay, is you can I mean you can think of this as written like this. Suppose you have a vector where the first term is nothing but x11 theta 1 plus x12 theta 2 plus x1p theta p plus theta p plus 1. That is the first term. The second term is xy2 minus x21 theta 1 plus x22 theta 2 plus x2p theta p plus theta p plus 1, so on. Yn minus xn1 theta 1 plus xn2 theta 2 plus dot dot xnp theta p plus theta p plus 1. So you can consider this vector, and you see this, I mean the yellow, I mean the one that I have marked in yellow is nothing but the 2 norm of this, 2 norm square of this, correct? This is, I mean the 2 norm square of this is nothing but the yellow marked thing. And so, and how, I mean what is a better way, I mean a very compact way of writing this? This can be written like, if you see, if you consider what y1, what y is and what x theta is, this is nothing but y minus x theta, and therefore your error becomes the 2 norm of y minus x theta whole square. Okay. Okay, so your error, you have got the error. Now let's say if the sum of square error is minimized. So what you need to find out is, you need to minimize with respect to theta y minus x theta whole square. Okay. Now any vector x, if you take the 2 norm of that, that can also be equivalently written as x transpose x, and therefore this can be written as minimization over theta y minus x theta transpose y minus x theta. Breaking this up, we can write this as y transpose minus, again the formula that I am using here is AB transpose equal to B transpose A transpose. So this becomes theta transpose x transpose into y minus x theta. This can equivalently be written as, now I am just breaking up the terms. So y transpose y minus y transpose x theta minus theta transpose x transpose y minus plus theta transpose x transpose x theta. Okay. Now you see you are minimizing over theta, so the first term would go away because this doesn't have any theta. So whatever you do to y, it won't change the value of your particular function. So you only have theta to work with. So you can remove the first 2 terms, the first term, and so let me get to the question again. Okay. Okay, and then what you need to do is, you need to take a derivative of this, because that is the way we know how to get the minimum value. So if you take a derivative of this, so the first term would be this term, and this term would basically be the same because x transpose y is equal to y transpose x, and therefore this will become minus 2, how have they written it? Okay, x transpose y, okay. Yeah, so we can write this equivalently, the first 2 terms we can write equivalently as 2x transpose y, because theta goes away when you are when you are taking a derivative with respect to theta, and the final term becomes 2x transpose x theta. Okay, this how this comes out to this is something which you have to, I mean this is something which you can take at face value right now, because this is vector calculus and you need to break up the matrix and do it properly, and then you will see that this will come out to be x transpose x theta, and 2 times is coming because there are 2 thetas sitting, that is why 2 theta is coming, and you are setting it to 0 because that is the way you calculate the minima or the extrema, and so this becomes x transpose x theta equal to x transpose y, and I believe that is the way the question has been framed, that finally which of the following equation will hold. You see that this equation is holding, and therefore the last option is correct. Okay, so I have gone through the questions. So now you can ask me any doubts, any basic doubts that you might have about linear algebra, because this uses linear algebra. So if you have not seen linear algebra before, you can ask me. I will give you a brief overview of what all things you might need in this particular course, and you might ask me any other questions also. So go ahead. This is, you can ask. Yeah.
Hi Soumya.
Yeah.
Could you explain the last step of derivatives? How did you take derivatives of those?
Yeah, see, so is this clear, how the first 2 terms became minus 2 x transpose y?
No.
See, so just consider this to be scalars, okay? So for now, let's consider to be scalars. So theta, yeah, so theta is a vector. So okay, no, don't consider scalars, let's stick with vectors. Okay, so when you are taking a derivative of y transpose x, you are taking a derivative with respect to theta, so that becomes y transpose x. Okay.
Okay, got it.
Yeah, so this, the first term becomes y transpose x, and if you take a derivative of x of theta transpose x transpose y, that again becomes x transpose y. Okay, sorry,
Okay.
that again becomes y trans, or you can write the other way, I guess. Just a minute. This is y. Okay, this is, okay, let me do this properly then. Okay, okay, y is n cross 1, x is n cross p plus 1, and theta is r of p plus 1, right? So y transpose x theta would be what? P plus 1, yeah, so this will be 1 cross 1, I believe. N cross 1 will go 1 cross n, n cross 1 cross, yeah, so this is, yeah, so this is nothing but a scalar. You see, this is nothing but this y transpose x theta is nothing but a scalar. Did you get that? That y transpose x theta is a
yeah, now I get it.
Yeah. So that is why when you are taking a derivative, you will get that is why you are getting this x transpose y from both the places, because once you are doing theta transpose x transpose y, the other time you are doing y transpose x theta. So since they are scalars, so you can just think of them to be the same. Okay, so
Thank you.
yeah, so any other questions? So are you comfortable with all this linear algebra, everything, everybody is comfortable with all these things, orthogonalization and all those? Okay, Yeah.
Can you give me
Yeah.
a brief introduction to eigenvalues and eigenvectors and what they actually mean when you multiply by an eigenvector?
I could understand eigenvalue, eigenvectors, and then the last part I did not get.
When you multiply a matrix by an eigenvector,
Okay.
they say
Okay.
it
Okay.
just
Hmm.
translates
Hmm. Hmm. Hmm.
change of direction. I don't understand that.
Okay. Okay. So let's see. Okay. So first of all, the first point that you need to remember is any matrix has to be square to have eigenvalues and eigenvectors. I am writing Evex for eigenvectors. So this is the first thing that you need to understand, that they must be square. Okay, you cannot have a rectangular matrix and have eigenvalues, eigenvectors for them. So eigenvalues, eigenvectors are special pairs. So especially eigenvectors. So generally let's start with eigenvectors. So that's the precise thing that you just said. That is the definition of eigenvectors. So let's say I have a matrix A, and this is the eigenvector of that matrix. If after multiplying that matrix, after multiplying this vector with A, if we have something like lambda v, that means that v, lambda and v are is eigenval eigenvector pair for A. Okay, that is the definition of how you define, or what you say an eigen vector is for a square matrix. Now what more? Yeah, do you have any doubts in this?
Be the same as lambda and v. The v's are the same
I am not understanding. There is some
by definition.
huh? Can you come again? I did not get your question.
In this equation,
Yeah,
both the v's on the left and right
are the
side
same.
are the same.
Are the same. Yes, they are the same.
Okay, that is the definition.
They are the same, and so I mean there is a, how can I say this? Okay, let's consider one matrix. Maybe I don't know whether I will be able to draw it. Yeah, so basically what you so see what happens is any matrix is a linear transformation. Okay, so what it does is you have a matrix, let's say A1, A2 up to AN, and this is a n cross n matrix. This is a square matrix, and you have multiplied it with something which is n cross 1. So the output of course will be n cross 1, and so whatever the direction this vector, this v vector in n dimensional space, so in 2 dimensional space is might point in this, after multiplying with A, if it continues to point in the same direction but it is just scaled by certain amount, then you consider this vector to be the eigenvector. This is the way the eigenvectors are defined. So yeah, so that is it about eigenvalues, eigenvectors. I can talk about more about them, but it is not really I mean within the scope of this course as of now. So yeah, okay. Okay, so any more questions?
How do you actually calculate the eigenvalue and eigenvector?
Okay, that's an interesting question. So that's a, see what happens is, as I said, you have AV equal to lambda v, and if your A is a n cross n matrix, you might end up with I mean you will end up with v1 to vn as eigenvectors. Now all these eigenvectors may not be different from one another, they might be just scaled scaled versions of each other. So what you can okay, let's say, okay, so I don't know whether you will be able to get this, but I will try my best. So let's say you have n eigenvectors and you have this matrix n cross n, and you have the set of eigenvectors. So these are the set of eigenvector, like every one of them is an eigenvector of this matrix. So this can be written as AV1. So this is another way to look at matrix multiplication. So you can look at this like that. So AV1 and so on up to AVN. Okay. Okay. So now you see that this AV1 is nothing but lambda 1 V1. So lambda 1 is the corresponding eigenvalue, and lambda 2 V2 and lambda n Vn. Okay. So we have AV equal to some matrix. You have some matrix delta into V. Now what is this delta? This matrix can be written in this form: lambda 1, lambda 2. This is a diagonal matrix where everything here is 0 except the diagonal elements, and you have again V1, sorry, I am writing it in the other. Yeah, so this can be written as V1, V2 up to Vn, and this is the diagonal matrix lambda n 0 0. So I am denoting this by V and this by this capital lambda. So this becomes V times delta. Okay, so this is the way you can okay, so yeah, so this is the way you can look at eigenvalues. Now you see what happens is, if you have so how can you, so your question was how can you find the eigenvalues, or so the first step that you need to do is need to find out the eigenvalues first, and for that eigenvalue you need to find out the eigenvector. So let's say you have A, V equal to lambda V. This is your equation. So you can put you can bring this lambda to the other side, and this becomes lambda I minus A to V, or A minus lambda I into V, whatever, A minus lambda I into V. Is this clear till now? Or maybe I should, what I should do is, maybe I should give you an example, maybe that will be clearer to you, because this might be a bit difficult. Okay, so let me start with an example. Okay, I'm sorry, this is this might become difficult, so let me just take a very simple example of 1 2 3 4. This is your matrix. Okay, so the way you go about is lambda, I was trying to prove why this is the case, but anyway I'll just go about doing this. So lambda I minus A, so you compute that, so that becomes there is a huge noise from somebody. Okay, lambda 0 0 minus 1 2 3 4, and this becomes lambda minus 1 minus 2 minus 3 and lambda minus 4. Okay, so you see, one thing is, as I told you, that for eigenvalues this will be AV equal to lambda V. That is the definition of eigenvalues and eigenvectors. So you have lambda I minus AV equal to 0, right? So whenever this matrix, this particular matrix turns out to be 0, that is the root, that is one of the eigenvalues. So when will this matrix turn out to be 0? You can find, I mean, the roots of this, the determinant of this. So yeah, so finally what you need to do is you need to take a determinant of this determinant of this, the determinant of this would be lambda 1 minus lambda minus 4 and minus 6 equal to 0. So the roots
Soumya,
of,
sorry to interrupt you.
yeah,
Could you explain or elaborate more on why we take determinant of this matrix? Why it is that when that matrix is 0, its determinant is 0 too? Could you
which matrix is 0? None of the matrices are 0. Okay.
no, the determinant is 0 when this
Okay.
equation holds.
Okay, so how to, do you know something about the null space of a matrix?
Yeah.
Yeah.
It's basically right.
Yeah, so you see what happens is when you have lambda I minus a, so the eigenvector lies in the null space of lambda I minus a. Okay, right? So that means that for that particular lambda, a is losing rank. So whenever a is losing rank, you want to find out. So the surest way of trying to find out how when a loses rank, that means the determinant of that matrix will be 0. When any matrix loses rank, then the determinant of that will be 0, and therefore what you can say is that whenever lambda is such a value, when the lambda I minus a is losing rank, we can say that the determinant of this matrix will be 0. So I am not, since I have not gone through the null space, rank, determinant and everything, I am just telling you of.
Understood.
Yeah.
So it's basically determinant is also some sort of area, right? It brings two dimension to
Correct.
if
Yes.
that kind.
Yes, precisely. And determinant is also an indicator of the rank of the matrix. So if your rank is 0, if your determinant is 0, that means for that your matrix is not full rank. And
Got it.
so that is why the determinant is linked to how we calculate eigenvalues. So I am not going through that, I am just giving you the gist of how it is calculated. Okay, so this becomes lambda 1 minus 5 lambda plus 4 minus 6, which is minus 2. I hope I am doing everything correctly. So lambda square minus 5 lambda plus minus 2, minus 2 is equal to 0. So let me just check. My matrix was 1 and 4. Okay, so I have got 1 plus 4, I have got 5 here, and 4 minus 6 minus 2. Yeah, so the solutions of these two, so the two roots of this particular equation would be the eigenvalues. So they will be what, 5 plus minus root over 25 plus 8 by 2. So these are the two eigenvalues, 5 plus minus root 33 by 2, and the corresponding vectors. And now once you get the lambda 1 and lambda 2, you can go ahead and do a minus lambda 1 I, and the null space of this matrix will give you an eigenvector for that particular. So I don't know whether you are aware of this, all these things. I am just giving you the gist of how to calculate. Okay, so
Thank you.
Okay, so yeah, so this is the way eigenvectors are calculated. So we have digressed to some other place today, but anyway, this is fine. Okay, so any more questions?
The YouTube link.
Okay, YouTube link. Okay, let me. Okay, how to get this? Okay. Yeah, I have pasted it in the chat box. Okay, somebody is asking what is orthogonalization. Okay, that is again a good question, but it would require quite a lot of work maybe. So I will try to answer it in the easiest possible way. So orthogonalization, the term means basically perpendicular. So it is nothing but a fancy term for perpendicular. So you have vectors. So let's consider vectors like 1, 2, 1, 3-dimensional vector, and let's consider another vector which is 1, 0, -1. Okay, this is x. Let's not write it in this way. You have x which is 1, 2, 1, and you have another vector which is 1, 0, -1, right? And then you take a dot product of this. So dot product is defined by, it's denoted by x comma y, and it is defined by x transpose y. So what you need to do is you take transpose of x and then you take a transpose of y, and you see this becomes 0. This means that whenever the dot product of any two vectors becomes 0, that means x and y are orthogonal. X and y are orthogonal. Okay. Now so x and y are orthogonal means the transpose of these two, this transpose x transpose y will become 0. Now let's say you don't have orthogonal vectors. Let's say I am taking two vectors and they are not orthogonal, like I am taking the same vector 1, 2, 1, and I am taking another vector which is let's say 1, 1, 1. I don't so x transpose y, if you calculate, it will not be equal to 0. In this case it is just the sum of 1, 2 and 1, it will be 4. So x and y are now not orthogonal. So but you want to keep x, but at the same time you want another vector z which is orthogonal to x. Okay, these are the two vectors that are given to you. So there is something, why is this necessary? So there is something which is known as span of a vectors. So these two vectors span something, so span some 3-dimensional space. So just consider that you want a vector z which is related to y in some sense, but which is orthogonal to x. So that is the problem that you are after. So okay, this might be bit calculation. Okay, so how to do this? Okay, so the first thing which you need to do is you need to take, I hope I remember this. Okay, so you need to normalize x. So you have x which is, and you denote and you divide it by the norm of the 2 norm of x. So the 2 norm of x is given by 1 plus 4 plus 1, which is root over 6. So you have 1 by root over 6, 2 by root over 6 and 1 by root over 6. So that is what your x is. So you see that x and x hat are basically the same thing, just scaled versions of each other. In the vector sense, they are the same thing, they are pointing in the same direction, but their magnitude of the second one is just 1. That's the only difference. Now what you can do is you can take a dot product of x hat transpose y, and that will lead you to have 4 by root 6. I hope this is clear. This is nothing but 1 by root 6, 2 by root 6 and 1 by root 6, and this is 1, 1, 1. So if you do this, it will come out to be 4 by root 6. Okay. Okay. So now what you can do is you can take x hat and you can subtract x transpose y, which is a scalar, times x hat. Yeah, I hope this is correct. This is 1 by root 6, 2 by root 6 and 1 by root 6, minus x transpose y would be 4 by root 6. Again this would be 1 by root 6, 2 by root 6 and 1 by root 6. So this becomes 1 minus 1 by root 6 minus 4 by 6, 2 by root 6 minus 8 by 6, 1 by root 6 minus 4 by 6, and okay, now this has gone out of my hand. So okay, I don't know whether this is okay, so let me just check one thing. This is 1 by root 6 minus 4 by 6 to 1 by root 6 plus 2 by root 6 into 2 by root 6 minus 8 by 6 plus 1 by root 6 into 1 by root 6 minus 4 by 6. This is 1 by 6 minus 4 by 6 root 6 plus 4 by 6 root 6 minus 16 by 6 root 6 plus 1 by 6 minus 4 by 6 root 6. So is this coming or something is happening here? Actually this should turn out to be I mean, however you do this, x transpose minus x transpose y into x bar, that should turn out to be 0, but I have done
the third term should be 4 by 6 root 6.
Which one?
The third term.
This term, is it?
The last line, third term, 4 by 6 root 6 plus 4 by 6 root 6, 1 by 6 minus 4 by 6 root 6 plus 4 by 6, it should be.
Okay, yeah, correct. That would be 4 by 6. That would be 4 by 6, and the rest of the terms. Okay, so let's see. This actually should have come out to be. Have I done something wrong here? Actually this should turn out to be 0. That's the essence of this. So this is also known as Gram-Schmidt orthogonalization. So maybe I have done something wrong, because I should have taken smaller vectors maybe, because this is coming out to be 4 plus 1 minus x transpose y x bar. 1 by root 6, 2 by root 6, x transpose y is 4 by root 6. X transpose y is 4 by root 6, that is fine, and x transpose x bar, which is 4 by root 6 into x bar, correct. Oh, there should be, let me just check one thing. There should be some other vector, is it? Let's check. Okay, minus. Okay, I have another vector, which is, okay, let me write it in plain terms. Okay, I'm sorry, let me try to work this out, because this I might have done something wrong. I'm not getting. So let's say I have two vectors x1 and x2. So my first vector is y1, which is x1 by the norm of x1. Okay, that is my first vector, and so okay, no, let me write it in this way. Okay, let me consider y1 to be x1, and let me consider z1 to be y1 by the dot product of y1 with y1 and a root over of that. So the 2 norm of y1, that is fine, and let y2 be equal to x2 minus, okay, I got it. This would be x2. Okay. This would be x2, sorry. Yeah, I understood the problem. Okay, so x2 and x2 comma z1 times z1. This would be the proper thing. Okay, so okay, this was wrong. This particular thing here was wrong. So till here everything was fine, then I messed up. Okay, I have to subtract it. Okay, yeah, okay, so this would be y minus x hat transpose y, so the component of y along x times x hat. Let's see what it comes. This would be 1 1 1 minus x transpose y is 4 by root 6, and this would be 1 2 1, and I can just put the roots, take the root 6 outside and say that this is 4 by 6. So this would be 1 minus 4 by 6, 1 minus 8 by 6, 1 minus 4 by 6. Now if you do with x, I believe now it should come to be, so now if you take a dot product of 1 minus, okay.
Soumya, could you just explain a little bit on when you said take subtracting x transpose y along with the component of x, just a little bit in terms of geometric intuition of that.
Okay. So see, what you are trying to do is, how can I, okay, okay, yeah, so what you are trying to do is, so suppose you have two vectors like this. Okay, you have two vectors like this. You have taken the first vector. You have taken the first vector. This is your first vector you have taken, but the second vector is not 90 degree perpendicular to this. So what you are trying to do is, so you can think of this like normally, like in a two-dimensional plane. So suppose you have two vectors which are linearly independent, then those two vectors will span the entire R2 space, correct?
Yeah.
And an equivalent way, so these two vectors will span the entire R2 space. An equivalent way of trying to find out another basis vector, let's say, would be the x-axis and the y-axis, correct?
Yeah.
So what you are trying to do is, you want to find, so these are your targets, that you want to find x-axis and y-axis. Your target is being that, what you can do is, I mean, what is the way, so what is one simple way of considering this vector? So let's say I have, this is my vector space, I mean R2 space, and these are the two vectors which have been added to give you this particular vector. And these are the two vectors that have been given to you. One is x1, which is nothing but the x-axis, and the other is x2. But you need to remove x2 and get y. So how can you get y? What you need to do is, you need to project x2 onto the x-axis, right? So once you project x2 onto the x-axis, you will get hold of this particular vector x1. And then what you can do is, you can subtract from x2 the component of x1, component along x1. You see, since x1 plus y, that had actually given you x2, if you get hold of this x1 and you subtract it from x2, you end up with y, and that is the reason why you get a orthogonal thing onto the.
Yeah.
Got
Thank
it?
you very much. It's a great explanation. Very, very good explanation. Thank you.
Yeah, but somehow I have messed up the calculation, so I apologize for that.
Actually, calculation doesn't matter. It's a concept matters, right?
Yeah, so you
thank
can
very
keep
much.
this in
Yeah.
mind. This will stay in your mind. So okay, let me again. I'm not understanding what I'm doing wrong. Okay, anyway, so I must be doing something wrong here. I'm not sure what I'm doing wrong. 1 minus 4 by 6, 1 minus 8 by 6, 1 minus 4 by 6, and if this is multiplied with 1 to 1, I don't know why I will not get 0. So 1 minus 4 by 6 plus 2 minus 16 by 6 minus plus 1 minus 4 by 6. So this is coming out to be 4. Oh, I have got this. Okay, yeah. So this turns out to be 0. Is this clear? I mean, it has become dirty, I know, but you see, this is the way you can do the this thing, how you can orthogonalize. So so my two vectors were x1, my two vectors were x1 and y1, and they were not orthogonal. So what I did was, the first step was, as I said here, the first step is to take this z1 to be y1 by this thing. So I have taken this, I have normalized this. So the norm of this x hat would be 1, and I am taking the x hat, and I am taking x hat transpose y, which becomes 4 by root 6. Now what I am doing is, as I said, so here is precisely what I drew in the diagram. I am precisely doing that. So you have got maybe these two vectors. Of course, these are 3-dimensional, but just consider it to be in the 2-dimensional plane. So what I am doing is, let's say I have got this. This was your x hat. Let's say this was your x hat, and this was your y. Now I am projecting y onto x hat, and I am getting this component. And if you want to get the two perpendicular things with which make up y, then what you need to do is, you need to take this component. So if you see, if I take a projection of this component, I have got this part, and y was basically some z plus x hat. I have already got something, I mean the component of y along x hat. So this part I have already got. So if I just subtract this from y, what I will be left over with is the perpendicular component. And you see that I have done y, this is y. I have taken the 4 by root 6, and I have just done this. I have just taken the projection of this and subtracted it from 1. I have ended up with this vector, this particular vector. And if you take a dot product of this vector with the original x, you see that you will end up with 0. So that means that this vector is indeed perpendicular to x hat. Is this clear to everybody? I messed up the calculations a bit, but is this intuition clear, and is the calculation clear?
Yeah, it's pretty clearly explained. Thank you.
Okay. So any more questions?
So I just want to understand the schedule. So this sessions, they're like regularly taken on weekends this time, right?
Yeah, every Saturday 7 to 9 I will be taking the session. There are other 3 TAs also. So they will, 2 more sessions are held on Saturday, 3 to 5 and 5 to 7, and another is held on Friday. I don't know the exact time for that. Okay, yeah, so and the same 10 questions will be, I mean 8 or 10 questions will be solved in all the sessions.
So all the sessions are same?
All the sessions, I mean from the questions point of view, all of them will be same, but after that it depends on what questions are being asked to the TAs. Depending on that, the rest of the material might be different.
Okay, and sir, this question set is included in our assignment. This
no, these are actually taken from last year's assignments, but your assignments this year should be similar to what we are covering in this sessions.
Okay, thank you.
Thank you.
Okay, so if there are no more questions, maybe I'll close the session. Okay,
Thank you.
thank you everybody for
Sir,
joining this.
is there any session on Sunday?
Sunday I don't think there are any sessions.
Okay.
Okay. Okay, so I will upload this video after this, and okay, so let's meet again on next Saturday, same time. Thank you everybody.
Thank you.
Thank you.
Okay, thank you, sir.